Alright, in this video in section 13.4 we're going to look at how we can go about interpreting second order derivatives. Okay, so in the last video we defined the second order derivatives and then saw that interesting result known as Clairaut's theorem that said that the mixed partial derivatives for a sufficiently nice function are going to be equal. Okay, so here I've just drawn our surface, and right at the point P, right, the slope of this purple tangent, right, at P, in other words, the slope of this orange trace curve here, this is going to just be the first order partial derivative of f with respect to x. It's just telling us, again, the slope of that hillside in the positive x direction. Likewise, then the slope of this pink tangent, which is our slope of this green trace curve, that's going to give us the y derivative, the first order derivative with respect to y at P. Okay, so how about, say, the xx derivative? What is that telling us geometrically? Okay, so over here on the right, I've gone ahead and just drawn our xz cross section. Okay, and so you can see there's that orange trace curve when x is a. And so we define, right, the xx derivative of f to be the x derivative of the x derivative of f. Okay, and now here's the deal, right? Partial f partial x, as we said over here, is just telling us the slope of our surface in the positive x direction. And now what are we doing to that thing? Well, we're taking its x derivative. Or put another way, what we're asking is, what is the change in this purple slope as we move in the positive x direction? Okay, so here for this xx derivative, we're really describing a change in a change, right? It's a change in the slope as we move in the positive x direction. Okay, now of course we could do this exact same thing for the y derivative, exactly the same interpretation there. So here the punchline is as follows. So our xx derivative will measure the change in the x slope as you move in the positive x direction. Okay, now another way you can phrase that in connection to what you saw in Calc 1, right, is that this change in the change, or in other words, this change in slope as we move along this orange curve, is really just describing what we call the concavity of the curve. Okay, so I can rephrase the top line there as saying, well, the xx derivative is really just measuring the concavity of our surface as we move in the x direction. Okay, so here for the way I've drawn this particular surface, right, given that this orange curve is concave down, that would tell me that the xx derivative for this particular surface at the point P would be negative. Okay, and then again for the y derivative, same interpretation. This is going to measure the change in the y slope, so the change in this pink slope as we move in the positive y direction. Okay, and that in turn would measure the concavity of our surface in the y direction. Okay, cool. So those are fairly straightforward. We at least can connect it back to something we already have seen in Calc 1, right? This idea of concavity. But of course, now what we want to do is look at the mixed partial derivatives. And so for this, right, well, we do have to be a little bit careful here, okay? So here, let's say I want to measure the yx derivative of f, which again by definition is just taking the y derivative of the x derivative of f. Okay, so here's the idea, right? So right now I've just included in my figure the tangent here at P in the x direction. So partial f partial x is just the slope of this purple tangent. And now what I want to know is, right, if I were to say move a little bit in the positive y direction, what's going to happen to that slope in the x direction? Okay, it's kind of a little bit of mental gymnastics we're applying here. So here's a way we can represent this, right? So I'm at P, and I can measure the slope in the x direction. That would just be the slope of the purple tangent. Then what I'm going to do is I'm going to move a little bit forward in the positive y direction. And then what I'm going to do is I'm going to measure the slope in the x direction again, right? And then I'm going to ask, well, how do these two slopes compare? Right? Am I getting more positive, more negative? What's going on there? Okay, so just to make this a little bit more concrete, let's say, for example, this slope here is -3, okay? And then the slope of this neighboring tangent, let's say, because it looks like it's a little more steep and it's still negative, so let's just say it's like, say, -5, okay? And let's say when I move in the y direction, let's say my little change in y, so here my little dy, my little change in y is, say, 0.1. Okay, so I just take a little step in the positive y direction, right? And now what I want to know is, how do these slopes compare? Okay, well, this is what we would say. We would say that the yx derivative at P would be what? Well, this is going to be a rate of change, so I'm going to put a little fraction bar here. And what I'm measuring the rate of change of, right, is this slope. So what I'm going to do is I'm going to take the final slope, which is -5. Then I'm going to subtract from that my initial slope, which was -3. And then I'm going to divide that by my little horizontal change, which is a change in the y direction. So I would divide that by the 0.1. Okay? So what is this? -5 plus 3, so that's a -2. And then I'm dividing that by 0.1, so that's really going to multiply that by 10. So I'd get -20 there for the yx derivative. Okay? Okay, cool. So now let's go ahead and make some conclusions here, right? So here, if I'm going to say measure the yx derivative, what I'm saying is I'm measuring, right, the change in my x slope as we move in the positive y direction. Okay, that's the yx derivative, and this is an example of how we would go about computing that. Now for the xy derivatives, just basically just swap the roles of x and y, right? This is the x derivative of the y derivative of f, so that's going to measure the change in the y slope as we move in the positive x direction. Okay, so that'd be like looking at slopes at P in the y direction, and then we're going to take a little step forward in the positive x direction, measure the slope again, and then see how those two slopes would compare. Okay, now the last thing I want to say is, well, remember Clairaut's theorem said that the two mixed partials are equal, at least for a sufficiently nice function. And honestly, I don't think that that's at all obvious if this is the way we're going to interpret these mixed partial derivatives, okay? So what I would like to do for the last part of this video is to look at like a discrete version, basically, of Clairaut's theorem, okay? So let's say I have, right, these 4 blocks, and these things are at various heights, and I'll go ahead and just make up some numbers just to illustrate how this is work. Let's say this is like a block of height 15, then over here we have, say, a block of height 12, and then let's do like, I don't know, 10 here, and then maybe 5 for the bottom one. Okay? So what does Clairaut's theorem look like for this discrete version here of what we're going to be measuring? Okay, so here's what we can do. Like, let's say, for example, I measure, so I'm standing on the blue block, and then I'm going to say go down to the this pink block at a height of 10, okay? So this would be a slope in the positive x direction, and this thing, I'll call this mx1. My first slope I'm going to measure in the x direction. And I'll just assume it's a unit step. So I'll right now just focus on the difference in the heights. So my final height is 10. My initial height is 15. So this would be a difference of minus 5. Okay? Well, then what I could do is, well, for the mixed partial, I'm going to take a step in the positive y direction and then measure the x slope again. Okay, so let's do that here. My x slope here, I'll call that mx2. And again, just assuming a unit step here. So I'm just going to do what? 5 minus 12, so that'd be minus 7. Okay, so now for the x derivative, okay, what would this be? Okay, so I'm starting off with an x slope of -5, and then my x slope one step over is -7. So now for this mixed partial, it's going to take the difference in these slopes. So this would be -7 minus a -5. And that's going to come out to be, well, -2. Okay, so now here's what Clairaut's theorem is really saying. It's saying that if you do this same kind of thing, but now do this, say, for y slopes, we should come out with the same value of -2. Let's try it out. So I'm going to go ahead and now measure, say, the slope here. So this is a slope in the positive y direction. So that'd be 15 down to 12. So this would be a slope of -3. And then here, I'm going to measure another y slope over here. So this would be my2. I'm going from a height of 10 down to a height of 5. So this would be, well, -5. And so, wait for it, we're saying what? Partial squared f of, this would be the xy derivative, would simply be the difference in these slopes. So that'd be what? -5 minus 3, and voila, right? These two things are coming out to be the same. Now, you might say, well, is that just because you chose really nice numbers here for the heights of these blocks? No, I just made these up off the top of my head as I'm filming this video, okay? I encourage you to just try this out with any heights. So put like height A, B, C, D, okay? And go through this calculation. You're going to find that the two expressions you get for the mixed partials are the same expression. This is always true, okay? And honestly, still, even with this picture, I mean, I think this is more believable. It's still maybe not the most intuitive thing. But what you can do, and I'm not going to actually prove Clairaut's theorem. It is in the textbook, but it's a little bit hard to follow. But really, the formal proof of the theorem uses this exact idea. They just do it in a more continuous fashion. They don't use these discrete blocks, but this really is the essence of what that theorem is stating. Okay, great. Well, in the next video, we're going to go ahead and look at an example of how to apply all this stuff on interpreting these derivatives. Okay, see you next time.